Hello everyone. Today we'll be solving the problem number 230. So, kth smallest element in a binary search tree. Right. So you can just go through the question, and they have given wonderful examples as well to understand the question. Right. So I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given the root of the binary search tree. You can clearly see here. We are given the root of the binary search tree and an integer k. So here and an integer k. You can clearly see here. We have been given an root of the binary search tree and an integer k. What is our main goal then? Our main goal is to return the kth smallest element in the BST. We have to return the kth smallest element. First least element. So suppose if we are having this thing integers in the array in the ascending order 1, 2, 3, 4. The least element is here the first element, right? I am considering a sorted array. So the least element will be within the 1, 2, 3, 4 as first least element is 1, second least element is 2, third least element is 3, like that it goes, right? So we have to find the kth least element that they have given here. So here k equals 1. The first least element we have to find here in the example. You can clearly see here. So here we have the elements 1, 2, 3, 4 and kth least element is obviously 1. That's what they have. We have to return in the output. Clearly you can see here output 1. Same goes with the example 2 as well here. Root equals 5, 3, 6 or something they have given here. Everything is fine. 1, 2, 3, 4, 5, 6 we have got here. K3 within the 1, 2, 3, 4, 5, 6, 3 is the third least element. We can clearly see. So the output will be 3 here. Right. So I hope this is clear. So what we have to find? We have to find the kth smallest element in the binary search tree. So let's understand the binary search tree property first. A binary search tree, this follows the rule. We know that one thing, left subtree's value, just give me a second here. Yeah, this one, left subtree value must be lesser than the root node and right subtree value must be greater than the root node. This is what the binary search tree rule says, right? So we have already solved the problems on the binary search tree. So by this time we have to know the rules of the binary search tree, right? So I hope this is clear. So binary search tree follows the rule, left subtree has to be less than the root value, right subtree has to be greater than the root value, right? So this is one thing. We have already discussed the example, right? Suppose for this one, it will be we can just make use of the or let me do one thing. Let's discuss this one in the approach. I hope the question is completely clear. So now let's discuss the approach. How can we solve the problem, right? How can we articulate that one in the form of code? Let's see that one in the approach and then followed by the edge cases. Let's discuss the edge cases one by one, then finally write the code and discuss the complexities of the code that we have written. As usual, let's start with the approach. Just give me a second here. So let's discuss the approach step by step. So the approach that will be going for this, the approach that will be using for this problem is in order traversal. DFS with in order traversal. I just give here in order traversal. DFS, right? We'll be making use of DFS with in order traversal. So a binary search tree in order traversal starts from this one. This has to satisfy the condition LNR. It starts from left, then node, then right. First we have to consider left, then we'll be considering node, then followed by the right. Why we are making use of in order traversal? You can clearly see here. In case of binary search tree, left we are having the smallest this one small value at the left subtree. Mid value will be here, this one root node, and the greater value will be at the right subtree, right? If we consider in order traversal starting from left node and this one right, we will get the value in the this one ascending order, right? So here you can see in this case, if we consider this one, we will get 1, 3, 4 here, right? So that is the reason we'll be considering in order traversal here. I hope this is clear. So what is the step here? This always gives the element in the elements in the sorted order. That is the reason we'll be making use of the in order, right? So this is one thing we have to keep in mind. So what is the steps here? Let's go with the first step. Let's discuss the first step. Nothing but we are performing an in order traversal. We have to perform an in order traversal. I'll just give here IoT in order traversal. So this is left node and right, just for the understanding purpose. Second thing, after performing an in order traversal, we have to store the elements in an array. Since in order directly gives the sorted order, as I've shown this one example clearly. So next thing is, after performing an in order traversal, we have to store the elements in the array. Store the elements in the array. Since in order traversal gives the sorted order, we are just storing the elements in the array. After storing the elements in the array, we have to return the kth smallest element. So that's what they have asked for. We have to return kth smallest element. So that's what we'll be doing here. This is the approach that we'll be going with. One more thing, when I say return the kth smallest element, we know that this is one indexed. Kth smallest element, whatever we have to consider, this is one index. This is not zero index. This one we have to keep in mind. It starts with 1. Basically, the binary tree indexing or the binary search tree indexing starts from 0. This here, kth smallest element, whenever we are finding this one, right, we are returning here in this approach. So here, this we have to consider one index, right? So this one we have to keep in mind. So this is the approach that we are going with. Initially, we have to perform an in order traversal. We know in order traversal will be performing first left node and right. This we have to keep in mind. Second thing is, after performing the in order traversal, we are storing the elements in the array. Why we are storing the elements in the array? We are not performing any extra steps, because since we are making use of the in order traversal, it gives the sorted array, right? So that is the reason. Second step, we can directly go for the storing elements in the array, in an array. So final step is we have to return the kth smallest element, nothing but one indexed, right? So here I hope the approach is completely clear. Now let's discuss the edge cases one by one. Just give me a second here. Edge cases, right? I let's do one thing. Yeah, let's discuss edge cases one by one now. So first edge cases, minimum nodes. I'll just give here minimum nodes. This is fine. First we are considering minimum nodes, means only one node in the binary search tree. So I can just write here only one node in BST. So let me consider here 10. This will be the root node, right? So k equals 1, suppose they have given, the output will be 10 in this case. The output will be 10, right? So we have only one element. So the output will be, when k is given 1, the output will be obviously only 10. I hope this is clear. This is for the condition minimum nodes. Only one node in the BST, right? Let's go with the second edge case, nothing but left skewed tree. So I'll just give here left skewed tree. When I say left skewed tree, it will be 5, 4, 3, 2, 1. Only left side we are considering, right? As it is a left skewed tree. Only left nodes we are considering. So this one is nothing but, let me do one thing. Just give me a second here. If I write this one correctly. 1, 2, 3, 4, 5. So we have only left nodes as it is left skewed tree. Suppose let's consider here k equals 3, right? So the output will be 3. Third least element we have to consider here. We have the elements 1, 2, 3, 4, 5. We can clearly see here. So the third least element here is this one, 3 in this case. I hope this is clear. This is the second edge case, nothing but for the condition left skewed tree. Let's go with the third edge case, nothing but a right skewed tree, BST. So I'll just give here right skewed BST. In this case also, let me make this one BST. binary search tree, left skewed binary search tree, right skewed binary search tree. I'll just give here in this case 1, 2, 3, 4 and 5. This is fine. This is nothing but right skewed binary search tree. Only right nodes we are considering. Suppose let's consider we have already considered 3, right? I'll give 4 here. So fourth least element is 1, 2, 3, 4 is this one, right? Fourth least element. So in this case, output will be 4. This is for the condition right skewed tree. Let's go with the final edge case or the fourth edge case, balanced binary search tree with k equals n. So I'll just give here, sorry, just give me a second here. Edge case 4, nothing but balanced BST. So here, let me give balanced BST with k equals n. Right, nothing but the last element. So we'll see this one with the example. You'll understand this one very clearly. So let me give here, when I say balance BST with k equals n, we have to go with, let me give here binary search tree we are considering, right? This will be 8 and this will be 2, this will be 4 and this has to be lesser, right? Let me consider 4. This has to be greater. Let me consider this one as 9. Suppose if I give k equals 9 here, k equals 5. Anything you can consider. I have already considered 3 and 4. So that is the reason I'm considering 5 here. So we are having the elements 2, 3, 4, 8 and 9 when we sort, when we involve this one in the in-order traversal. So k equals 5 they have given. So elements are duplicate. This is fine. We are just considering the when we involve this one in the in-order traversal, we will be getting this one 2, 3, 4, 8, 9. So among this one, we have to find the fifth least element, right? K equals 5 they have given. Fifth least element here is nothing but 9. The output will be 9 in this case. Sorry. Yeah, the output has to be 9, right? Yeah, the output has to be 9 in this case. This is correct. So I hope this is completely clear. This is for the condition balance BST with k equals n. Nothing but the last element. Nothing but we have got the last element as the output here. This is fine. What are all the edge case that we have discussed now? The first edge case was for the minimum nodes. The second edge case was for the left skewed tree. And the third edge case was for the right skewed tree. And the final one was for the balanced binary search tree with k equals n last elements. I hope all the edge cases are clear here. So next, let's start writing the code. So let's start writing the code. So in most of the previous problems, we have considered the recursive approach, right? So we have done many problems using the recursion. For this problem, let's go with the stack as we are making use of the in-order traversal, and let's make use of the stack here, right? So usually for the binary search tree or the binary tree problems, you can either solve the problems using the DFS, or you can solve using the BFS as well. You can either solve it using the DFS or BFS. Any approach you can go with. In my opinion, try to avoid the this one recursion as much as possible. You can get the memory errors that is related to memory sometimes. So if possible, try to go with the stack and this one stack as much as possible. So recursion, usually implementing the recursion is easier comparatively. So for this particular problem, let's make use of the stack, right? Iterative approach. Stack with in order traversal, right? So first thing is we'll be making use of the stack. So a stack for the let's initialize the stack here to empty array. This is fine. Next step, we have to start from the root, right? Let me consider variable current and let me initialize this one to the root, as we have to start from the root. And we need the counter to track kth smallest element. So let me consider the count as variable and let me initialize this one to the 0. The next step is while current not equal to null, means the current value is not equal to null and the length of the stack is greater than 0, then only we can proceed further. So this one we can consider within the while loop. So while current not equal to null and length of the stack is greater than 0, what we have to do? First step, we have to go to the leftmost node. So we are performing an in-order traversal, right? So left, middle, left, then root, then right, right? Left node and then right. This is what this one we have to consider. So first we have to consider the leftmost node. I can write in this while current not equal to null, what we will do? Let's push the current value. So I'll just give here to the stack, right? Let's push the current value to the stack. So I'll just give here stack dot push out current. Then let's assign the current to current dot left here. This is fine. Then after this step, we have to process the current node. So we have considered the leftmost node in the as first step. Then second step is we have to process the current node. So we have to remove the current one from the stack, right? And increase the count. So how can we write that one? We have to remove. I'll just make use of the pop here. Current equals stack dot pop, right? Then we have to increase the count. This is fine. Next step is after increasing the count, step 3 is if we reach the kth smallest element. Suppose if we have reached the kth smallest element, then we have to return it, right? So we are finding the kth smallest element itself. So if we reach the kth smallest element, we have to return it. So this is simple if condition. If count equals k, then return current value of the current, nothing but current dot val here. So next, finally, we have to move to the right subtree. So just give here current equals current dot right. After the final step is we have to move to the current, we have to move to the right subtree, right? So just assign the current to current dot right. So final step here is, we have already discussed this one in the edge case. If when k is invalid, it should never happen, right? So when k is, if k is invalid, then we have to just return -1 in this case. So let's give here return -1. Let me format the code once and hit the run button. So this is giving us wrong answer. Why, what's wrong? Let's check what is wrong. Make it. So what I have done wrong here is in the line number 6, it current value should not be equal to null or stack dot length greater than 0. Here instead I have made use of the ampersand, right? So I'll just make this one, or stack dot length of the stack greater than 0. Let me hit the run button again. So now you can clearly see the sample test cases are getting passed. Let me hit the submit button. So now all the test cases are getting passed here. You can clearly see. So the code works absolutely correct, right? In this case. So let's discuss the time complexity and the space complexity of the code that we have written. The approach that we went with here is iterative in order traversal, or we can just call it as iterative in order. So that's the approach that we went with. So what will be the time complexity here? The time complexity would be here big O of n, because we are traversing each node once in order traversal. In order traversal. So we are just traversing through each node once in order traversal, right? So overall time complexity would be big O of n. Again, I'm telling we are traversing here. Clearly see, you can clearly see we are traversing each node once in order traversal. So the overall time complexity would be big O of n. What would be the space complexity here? We have we have already discussed this one while we solved the problems using the recursion. So what would be the space complexity here? Space complexity would be, in this case, big O of h. Why? Because stack stores at most h nodes. H, we know that h is nothing but the height of the tree, or the tree height in this case, right? So that space complexity would be big O of log n for the balanced trees, and it is big O of n for the skewed trees. it's better to consider the better to consider the height of the tree rather, right? So it would be big O of h in this case, space complexity. So overall space complexity would be big O of h, and overall time complexity here would be big O of n. I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.